we can go through the magnetic effects of electric current. As we know, till the beginning of 19th century, the scientific world believed that both electricity and magnetism were entirely two different branches of physics. After the discovery by the Christian Oersted in 1819, we realized that the electricity and magnetism are closely related. So, in the experiment by the Christian Oersted, he showed that a pivoted magnetic needle could be deflected by a current carrying conductor placed near to it. So, in the figure we can see there is a current carrying conductor and a magnetic needle is placed very near to it, and when we switch on the circuit, there is a deflection in the magnetic needle. Since there is no other magnetic substances near to the magnetic needle, the deflection caused by the magnetic needle is due to some other magnetic forces. Here there is only the possibility that when we switch on the circuit, the current is flowing through the conductor and there should be a magnetic field. That magnetic field is influencing the magnetic field of the magnetic needle. So, from this experiment, we realized that the electricity and magnetism are closely related, and we can produce the magnetism from the electricity. We can have a close look into the experiment. We can go through the video. Now this is an experimental setup, and here this is a source of current, and when we increase the current, you can see the magnetic needle just near the conductor is deflecting, and when they increase the current, the deflection also increases. Now we switch off the circuit. What happened? The needle reaches its original position. Now we change the polarities. The positive and negative polarities are changed, and then switch on the circuit. Here the deflection, again the needle is deflected, but the deflection is in the opposite direction. Again also when we increase the current, the deflection also increases. After the discovery of the Christian Oersted in 1890, a relationship between the current in a conductor and the resulting magnetic field at a point near to it was established by the two scientists. That is, they are called the Jean-Baptiste Biot and Felix Savart, and they derived that relation in 1820, just after the Christian Oersted's discovery. And this relation between the current and the resulting magnetic field is called Biot-Savart Law. We can go in detail what the Biot-Savart Law says. This law helps us to determine the magnetic field at a point due to a small current carrying element of the conductor. Now this is AB is a conductor which is connected to a cell so that an electric current flows through it. In the figure you can see Mn This Mn is a very small segment of length dl of the conductor, and the length of the dl is very small compared to the total length of the conductor. Now there is a point P which is at a distance small r from the middle point Q of the segment dl, and also here theta. Theta is the angle between the segment dl and the distance r. And Biot-Savart Law, it states about the magnetic field at the point P due to this current carrying element, and we can go in detail. And the Biot-Savart Law states the magnetic field dB is the magnetic field due to this small segment dl, and this magnetic field dB produced by the elementary length dl of the current carrying conductor at the point P is directly proportional to the current I. That is, when increase the current I, the value of dB at the point P is also increases, and dB is also directly proportional to the elementary length dl. So when we increase the length dl, the dB is also increases, and dB is also directly proportional to the sine of the angle between the dl and the line joining the midpoint of the dl and the point P. That is, it is proportional to sine theta, and dB is inversely proportional to the square of the distance r between the middle point of the segment and the point P. Here, as this distance r increases, the value of dB also decreases. So this relationship is given by the Biot-Savart, and we can have the mathematical expression. We can express the dB is directly proportional to I dl sin theta by r square. Here the dB is inversely proportional to r square, so r square comes in the denominator. Now let us remove the proportionality. Then we have a proportionality constant k. Then the dB equal to k into ideal sin theta by r square. Ideal sin theta by r square. Here k is a constant, and if we SI units are employed, the value of k is 10 raised to negative 7. The value of k depends on the system of units chosen and also on the nature of the medium in which the conductor and the point are situated. Now in the case of a free space or in air, it is convenient to write the constant k in a different form. That is, k is equal to mu 0 divided by 4 pi. Here the mu 0 is called permeability of the free space. Mu 0 is called permeability of the free space. Permeability means it is the property of the medium in which how much the medium allow the passage of the magnetic field. Okay, so in the free space, the value of permeability mu 0 has a value that is equal to 4 pi into 10 raised to negative 7 Newton per ampere square. So in the free space, we can rewrite the Biot-Savart law like this. dB is equal to, instead of k, we can write dB is equal to mu 0 divided by 4 pi ideal sin theta by r square. Also, when we substitute the value of mu 0 as 4 pi into 10 raised to negative 7, then dB is equal to 10 raised to negative 7 into ideal sine theta by r square. Here, the intensity of the magnetic field. dB is the magnetic field, that is the intensity of the magnetic field. It is also called magnetic flux density. It is also called magnetic flux density. What is the unit of the magnetic flux density or the intensity of the magnetic field? The SI unit of intensity of magnetic field is Tesla. It is called a Tesla. We can also express 1 Tesla is equal to 1 Newton per ampere meter. 1 Newton per ampere meter. So this unit, that is 1 Newton per ampere meter, that we can derive from the one equation that we can see in the later section. But this Tesla is a very large unit. In the daily life, in the daily experiments, we can see the value of magnetic field. The intensity of magnetic field is very smaller than the 1 Tesla. So in the day-to-day practice, we are using the another unit for the intensity of magnetic field, that is Gauss. The smaller unit is Gauss. Here 1 Gauss and is equal to 10 raised to negative 4 Tesla. 10 raised to negative 4 Tesla. And magnetic flux density or the intensity of the magnetic field, it is a vector quantity. That means it has both a magnitude and a direction. The magnitude is given by the Biot-Savart law. We have the expression dB is equal to mu 0 divided by 4 pi ideal sine theta by r square. What about the direction? The direction of dB is perpendicular to the plane, containing the current element and the point P. So the direction of dB is perpendicular to the plane containing the current element and the point P. So the direction of the magnetic flux due to a current carrying conductor, that can be determined by using a law known as the right hand grip rule. So with the help of this right hand grip rule, we can determine the direction of the magnetic field. So let us go through the what states the right hand grip rule. It is also called right hand palm rule. So we know when a current flows through a conductor, a magnetic field is produced around it. So here in the figure you can see here the conductor is placed in your right hand, and the thumb, if the thumb along the direction of the current, then the other fingers gives the direction of the field. That is the right hand grip rule. If a current carrying conductor is held in your right hand with the thumb pointing the direction of the current, then the remaining fingers encircling the conductor gives the direction of the field. Okay. So from the figure you can see the direction of the magnetic field. So in a plane perpendicular to the conductor containing the point, the field lines is circular around the conductor. So the magnetic field around a current carrying conductor is, the field lines are circular, and the direction at a particular point, suppose we have to find the direction of the magnetic field, at this point, at a particular point, then you can see that it is, we can find so here the field lines are circular field lines. So if we wanted to find the direction of the magnetic field at this particular point, then what we have to do? We have to draw a tangent. So this along the tangent gives the direction of the magnetic field at a particular point. Now we are going to find the magnetic field due to a straight current carrying conductor. The magnetic field due to a straight current carrying conductor. Let's consider a straight conductor AB carrying a current I. Let P be a point at a distance, at a perpendicular distance A from the conductor. And we are going to find out the magnetic field at the point P due to this entire current carrying conductor is obtained by using the Biot-Savart law. Okay, we know we can consider a conductor is made up of a large number of the elementary length joined one by one. So the field due to each element, can be determined using the Biot-Savart law. So we can divide this entire conductor into a small number of the a large number of the small elementary length. So to find the point magnetic field at the point P, we have to find the magnetic field at the point P due to this small current carrying element. So then we have then the total magnetic field at the given point is obtained as the resultant of the contributions from all such elementary current elements. So this method, this integration method is using in this case. So here AB is the conductor, and it is the current I is flowing through it, and we have to determine the magnetic field at the point P. So for that we are dividing this entire length into a small elementary length, and using the Biot-Savart law we can find the magnetic field at the point P due to this small elementary length. Okay, and for that we can use the, let phi 1 is the angle subtended by the subtended at the point P, and also phi 2 is the angle subtended by the point A at the point P. Okay, so using the method of integrations we have discussed earlier, we can find the total magnetic field at the point P. So we are not going the detailed the integration steps. Here we have just the result. The total magnetic field due to the entire length of the conductor AB is obtained as capital B is equal to mu 0 divided by 4 pi A into sin phi 1 plus sin phi 2. Here what is mu 0? That is the permeability, I is the current flowing through the conductor, and A is the perpendicular distance from the conductor to the point P, where we have to find out the magnetic field, and phi 1 and phi 2 are the angles subtended at the point P by the end points A and B. Okay, now what is mu 0 divided by 4 pi? The mu 0 divided by 4 pi is equal to 10 raised to negative 7. So we can also write capital B is equal to 10 raised to negative 7 into I by A into sin phi 1 plus sin phi 2. Okay. Now if we assume that if the conductor is very long, then phi 1 and phi 2, these are the angles subtended at the point P by the two ends A and B. So you can imagine that if the conductor is very long, then the angle subtended at the point P by the end A, that is become approximately equal to 90 degree. Similarly the case with phi 1 also. So if the conductor is very long, we can assume that both phi 1 and phi 2, that is approximately equal to 90 degree. Okay. In such cases, what happened to the sin phi 1 plus sin phi 2, sin 90 plus approximately sin 90, here that is equal to 2. Sin phi 1 plus sin phi 2 equal to 2. So for a very long conductor, the capital B becomes B is equal to the mu 0 I divided by 2 pi A. So when we compare in this, the first equation, here this become 2, then we can divide 2 here. So mu 0 I divided by 2 pi A, mu 0 divided by 2 pi A. And also we can use the second equation. Here the B, this expression becomes B is equal to 10 raised to negative 7 into 2I by A. So this is the magnetic field due to a straight current carrying conductor. Next we are going to find the magnetic field due to a circular coil carrying a current. Consider a single turned circular coil of radius A carrying a current I. So in the figure you can see this is the circular loop in which the current I is flowing, and P is the center of the circular coil, and A is the radius. So from the Biot-Savart law, the magnetic field dB at the center of the coil due to an elementary length dl. That is, here the dl, as we have stated in the previous case, here the entire circular loop is divided into a number of the small elementary length dl. First we are going to find the magnetic field at the point P due to this small elementary length using Biot-Savart law. Then since this entire loop is made up of this small elementary length, to get the total magnetic field, we are going to find the by adding the magnetic field at the point P due to this all the elementary length. Okay, first we have to find the magnetic field at the point P due to this the small elementary length dl by using Biot-Savart law. So the dB is equal to, that is the magnetic field at the center of the coil, that is at the point P, due to the dl. So dB is equal to mu 0 by 4 pi into ideal sin theta by r square. Here the angle between the length dl and the distance a, or here the distance here r is the radius, and we are here the expression in this later we are changing r equal to the small a, that is the radius. Here the length angle between the dl and a is 90 degree. Then the dB becomes mu 0 divided by 4 pi ideal by a square. Okay, here a is the radius, and also the angle between a and dl is 90 degree. Here the direction of dB is along the coil and is inwards for the clockwise direction of current. That we can verify by using right hand grip rule. Okay, so you can take your right hand and you can encircle your fingers along the direction of the current. Then the thumb will give the direction of the magnetic field. Okay, so in that case, when you encircle the fingers in the direction of the clockwise direction, then you can see the thumb is pointing inward. The thumb is pointing inwards, so that is the direction of the magnetic field. For all elementary segments comprising the coil, then the angle between the dl and the radius a will be 90 degree. So the total magnetic field at the center is, we are going to make the summation. The total magnetic field at the center is B is equal to sigma mu 0 divided by 4 pi ideal by a square. Here the symbol, here the summation, the symbol sigma, that is used to denote the summation for all the elementary segments of the coil. So regarding the terms in the expression, here the mu 0, 4 pi and also a, all these are the, and I, all these are the constants. So for a given current carrying coil, I is a constant and the radius is also a constant. Mu 0 by 4 pi is already a constant. So here the summation is applicable only to the dl. So we can rewrite the B is equal to mu 0 I divided by 4 pi a square into sigma dl. Okay, here the sigma applicable only to the dl. dl is the only the variable parameter in the expression. All other terms are constants. So what is sigma dl? Sigma dl is the total length of the circular coil. That is sigma dl equal to 2 pi a, the circumference of the coil. So we can again write the expression for B, that is mu 0 divided by 4 pi I by a square into 2 pi a. That is B is equal to mu 0 I divided by 2a. Now this is the expression for the magnetic field at the center of a current carrying circular coil. Okay, if the coil has n number of turns, then each turn produces its own magnetic field at the center. So the total magnetic field at the center is mu 0 ni by 2a. So n times of mu 0 I by 2a, that is mu 0 ni by 2a. Okay, since mu 0 is equal to 4 pi into 10 raised to negative 7, we can also express B is equal to 4 pi into, instead of mu 0 we can substitute 4 pi into 10 raised to negative 7 into ni by 2a. A by 2a. Now the detailed calculations shows that the magnetic field intensity due to a circular coil decreases rapidly along the axial line as with the distance from the center is increased. So at the center of the coil we have an expression mu 0 ni by 2a. but we move along this axial line from the center, then we can calculate the value of magnetic field at every point along this axial line. Then we can see that this magnetic field is decreases very rapidly. Okay, and the expression for the magnetic field at any point along this axial line is given by the expression Bx equal to. So if at the point P, if the point P, which is at a distance x from the center of the coil along the axial line, then the value of magnetic field at the point P is given by Bx equal to mu 0 Nia square by 2 into a square plus x square all raised to 3 by 2. That is Bx equal to mu 0 Nia square divided by 2 into a square plus x square all raised to 3 by 2. So at this point we are not going to the derivation of this expression. We just have this final result. So from this expression we can see that as the distance from this center, that is the value of x, increases, the Bx, the magnitude of the magnetic field, is decreases very rapidly. So this is a graphical representation of the variation of magnetic field with the distance x from the center of the coil. Now we can have, when a current carrying, and what happened to a current carrying conductor is placed in a magnetic field. When a current carrying conductor is placed in a magnetic field, what happened is that there is a force acting on that conductor, and as a result the conductor is in motion. The figure we can see, there is a current carrying conductor is placed. So I is the current flowing through the conductor, and it is placed in a uniform magnetic field. The magnetic field are represented by the field lines. You can see the arrow marks, that is the direction of the magnetic field. So this equally spaced field lines represents the uniform magnetic field. Okay, here the conductor is placed, a current carrying conductor is placed in a uniform magnetic field B, and with an angle, his conductor is making an angle theta with the direction of the magnetic field, and L is the length of the conductor. Okay, so when a current carrying conductor is placed in a magnetic field, what happened to it is that a force acting on the conductor, and the conductor will be in motion. Okay, and the value of the force, the magnitude of the force acting on that conductor is given by the expression F is equal to BIL sin theta. F is equal to BIL sin theta. Here B is the magnitude of the magnetic field, I is the current flowing through the conductor, and L is the length of the conductor. And what about theta? In the figure you can see the theta is the angle between the direction of the magnetic field and the current directions. Okay, so this is the final expression. Here also we are not going the derivation of that equation. Okay, so from the figure we can see that here when we place the conductor in a perpendicular direction, what will happen? The theta will be 90 degree. So when theta will be 90 degree, the force acting on that conductor will be maximum. Okay, so when we place the current carrying conductor in a perpendicular direction to the magnetic field, then the force acting on that conductor will be maximum. Then the maximum value of the force F is equal to BIL. F is equal to BIL. Okay, now what is the direction of that force? the force is a it is a vector quantity. Here the force, magnitude of force is given by BIL sin theta. And what is the direction of that force, or in which direction the conductor moves? Okay, that is given by we have another rule that is called Fleming's left hand rule. It is called Fleming's left hand rule. Okay, you take your left hand and the stretch your thumb, forefinger and the middle finger in a mutually perpendicular directions. Then the and if we assume that if the forefinger is pointed in the direction of the magnetic field, while the middle finger is in the direction of the current I, then the thumb will give the direction of the motion or the direction of the force. This is what Fleming's left hand rule says. So take your left hand and stretch the middle finger, forefinger and thumb in mutually perpendicular directions. That is, you can see that is along the x and y z x, y and z directions, the three mutually perpendicular directions. And if the forefinger represents if the forefinger is pointed in the direction of the magnetic field, the middle finger represents the direction of the current I, then the thumb represents the direction of motion or the direction of the force. Okay, so using this Fleming's left hand rule, we can find out the direction in which the conductor moves or the direction in which the force acts. Okay, so let us say once again, if the thumb, forefinger and the middle finger of the left hand are stretched to be perpendicular to each other, and if the forefinger represents the direction of the magnetic field and the middle finger represents the direction of the current I, then the thumb represents the direction of the motion or the direction of the force. Okay, from this Fleming's left hand rule, we can find the direction of the force. And from this expression, F is equal to BIL or F is equal to BIL sin theta, we can find the another unit of the magnetic field. That is, we know F is equal to the maximum value of the force, F is equal to BIL. From that, B is equal to F by IL. Okay, so using this relation, we can have the unit of the magnetic field is the Newton per ampere meter. Because F divided by IL. So is another unit of magnetic field that we can obtain from this relation, that is Newton ampere meter.